There's this prevailing mantra in the world of technology right now. We hear it constantly.
Big data.
Exactly. Big data. It's the religion of the AI age.
Mhm.
Feed the beast. Give the model the entire internet, every book ever written, every Reddit comment, and, eventually if you just shove enough data into the furnace, the machine gets smart.
Right, it's the brute force approach, the idea that quantity has a quality all its own.
Mm,
And that's really been the governing philosophy for, what, the last decade?
for sure. But today, we're doing a deep dive into a case study that, well, it suggests the exact opposite. It's a bit of a contrarian take. What if the secret to teaching a machine a new language isn't reading a million bad sentences, but maybe just reading a few thousand perfect ones?
It's a classic quality versus quantity debate, but applied to something very specific and very difficult, building a parser.
And, okay, just so we're all on the same page here, because I'll admit, I had to, double check this myself when I first looked at the papers. When we say parser, we're not just talking about Google Translate, right? This isn't just swapping hello for hola.
Oh, not at all. No, translation is surface level.
Oh.
You can translate word for word and still speak complete gibberish. A parser is about understanding the deep structure,
The grammar.
the grammar. It's a piece of software that can look at a sentence and draw the diagram. It knows this noun is the subject, that verb is the action, and this adjective modifies that noun. It's the grammatical skeleton that holds all the meaning together.
Which is easy if you have English. I assume we have plenty of skeletons for English.
Incredibly easy for English, yeah. We have what are called tree banks, and these are massive databases where, armies of PhD linguists have sat down for decades and hand-labeled the grammar of millions of sentences. They've drawn all the arrows for us, so the computer just cheats off the answer key.
But, and here is the problem of the have-nots. If you want to build a parser for, say, Maltese, or a specific dialect of Quechua, or even a major language that just hasn't had that investment,
Then you're in trouble. You don't have the budget to hire an army of linguists to label sentences for 5 years. You are what we call low resource. And this is a huge issue because if you can't parse the language, you can't really build sophisticated AI tools for it.
So that is the problem we're trying to solve today. We are breaking down a really fascinating research paper. It's titled Dependency Tree Projection via Diverse Alignment Symmetrizations. It's by David Marejczyk from Charles University in Prague.
And I know the title sounds terrifyingly technical, alignment symmetrizations. It sounds like something from a physics textbook. But the core idea is actually very intuitive. It's all about shortcuts.
It's about using a language the computer already knows, like English, to teach it a language it doesn't know. The concept is called dependency tree projection.
Yeah, think of it like a transparency sheet. You take the grammatical tree structure of an English sentence, which we know is correct because we have those tree banks, and you try to lay it over a translation of that same sentence in another language. You project the grammar from the known to the unknown.
Like a stencil, you have the drawing in English, you place it over the German words, and you just trace the lines.
Exactly like a stencil. But, and this is the crucial point in Marejczyk's paper, he points out a huge flaw in how people were doing this before. They were trying to make the stencil too perfect. They were treating the connection between, English words and foreign words as a black and white issue.
And Marejczyk's argument, if I'm reading this right, is that we need to embrace the gray area. We need to get messy.
He says if you want to build a better robot, you have to get messy with the data first and then get incredibly strict later. It's a two-step dance.
Okay, let's get into the mechanics of this. Because to project grammar, to use this stencil, you first need to know which words match up. If I have the English sentence, the dog barks, and the German translation, I need to know dog equals Hund before I can even think about drawing an arrow to it.
Right. You need to align the words. And the standard tool for this, the real industry workhorse, is something called GIZA++hum.
GIZA++ up. That sounds like a generic 90s video game console.
It's almost as old. It stands for, well, it's complicated, but it's a statistical word alignment tool. You feed it a parallel text like, say, the Bible or UN documents in 2 languages, and it just crunches the probabilities to figure out who is dating who, linguistically speaking.
But here's the catch that I found fascinating, and it's totally central to Marejczyk's whole thesis. GIZA++ is opinionated, and it changes its mind depending on which direction it's looking.
That is the critical part. Alignment is inherently asymmetric. If you ask GIZA plus BD, what is the best German match for the English word bank? It might say bank. But if you ask it the other way, what is the best English match for the German word bank? It might get confused and say bench or seat. depending on the context.
Right, because languages aren't just one-to-one secret codes. You can't just swap words.
Never. You have idioms, you have articles, helper verbs. English has do support, do you like this? A lot of other languages don't have that. So traditionally, researchers looked at this asymmetry, this confusion, and they said, this is noise, we need to clean it up. And they would symmetrize the list using the most conservative method possible.
They play it safe. They look for the intersection.
Yes. They say, I will only trust a link if GIZA++ agrees in both directions. If English points to German and German points back to English, we keep it. Everything else, trash.
That seems logical, though. You want the gold standard links. You don't want to guess.
It is logical for translation, sure. If you're building a dictionary, you want to be certain. But Marichkik argues it is terrible for projection.
Why? Why is being sure a bad thing here?
Because of the goal. Remember, we're trying to drape this English grammatical skeleton over the entire foreign sentence. We need to cover the entire body. Every single word in that foreign sentence needs a job. It needs a grammatical parent.
Ah, I see. So if you only use the gold standard intersection links, you're going to have a lot of foreign words that are just orphans. They didn't make the cut, so they have no structure attached to them?
Precisely. You end up with a Swiss cheese grammar. You have holes everywhere. You might know where the nouns are, but you miss all the prepositions and adjectives because their alignment wasn't perfect.
So what's the solution?
So Marichkik composes something that I think is really clever. He creates a hierarchy. I like to think of it as 3 tiers of trust.
A priority queue. So he's basically telling the computer, hey, don't give up so easily.
Exactly. He tells the algorithm, I need to find a partner for this English word. First, check the intersection. That's tier 1.
But the gold standard, if it's there, take it.
But if it's not there,
Yeah.
and often it won't be, don't just stop. Go to tier 2, the neighbors.
This is the method with the fantastic name grow diag final and...
GDFA for short. Yeah. It's a heuristic. It basically says, okay, we know table maps to Tisch. That's a lock. Now, the word next to table is the. The word next to Tisch is der. Even if the algorithm isn't 100% sure, it's a pretty safe bet that the and der go together because they're neighbors to a known couple.
It expands the trust circle by holding hands. If you're standing next to a verified match, you're probably a match too.
That's a great way to put it. It fills in the gaps around the strong words. But even that isn't enough to cover everything. And this is where Marichkik really breaks from convention. Tier 3. He uses the X to English alignment.
Where X is the foreign language.
Right. He looks at the directional alignment from the foreign language to English.
Why is that direction so special? Why not English to X?
Because we need to ensure every foreign word is accounted for. Think about it. English is the source. If you look English to X, you might find that 5 English words map perfectly. But there are, say, 3 extra words in the foreign sentence that English just ignores.
Like a particle that indicates a question, or maybe a politeness marker. Japanese has those, right? Or cases. English doesn't have cases, so English to X would just skip right over that.
Exactly. The English word question might not even exist. But the X to English alignment forces the issue. It asks that little foreign particle, hey, I know you don't have a perfect twin, but who are you closest to in the English sentence? It forces a connection, even if it's weak.
So we're prioritizing coverage over perfection, at least at this stage. We'd rather have a weak link than no link at all.
In the building phase, yes. We collect all these messy, diverse alignments to ensure we can build a complete, unbroken tree. We just want to make sure every single word has a parent.
Okay, so we have our messy list of connections. We've built our tiers of trust. Now we have to actually run the projection. We have an English tree. We know cat is the noun, sat is the verb. How does the computer transfer that hierarchy to the German words?
It uses a recursive function. And for those who aren't coding wizards, you can just think of it like climbing a tree. You start at the trunk, the root of the sentence, usually the main verb, and you climb down branch by branch all the way to the leaves.
A depth-first search.
Depth first. And for every English word it visits on this journey, it checks that priority list we just made. It asks, who are my foreign counterparts?
This seems straightforward until you hit the real world. Because translation is never one word for one word. The paper brings up one-to-many relations. And the example they use is the English word indeed.
That's a great example. English, indeed. One word. The German translation is in der Tat. 3 words. Literally, in the deed.
So the English tree has 1 node. The German tree needs 3. How does the algorithm decide who's the boss of that new phrase?
It goes right back to the tiers of trust. It looks at the words in, der, and tat. It checks the alignment. And it finds that tat, meaning deed, matches indeed via the intersection. That's tier 1. That's a strong link. In and der only matched via the weaker tiers.
So tat wins.
Tat wins. It becomes the main counterpart. The algorithm makes tat the head of that little cluster, and then it hangs in and dir underneath it as its children.
That's really elegant. It preserves the structure. In-dir tat acts as a single unit, just like Indeed.
It works beautifully. It keeps the grammar logical.
Yeah.
But then you have the nightmare scenario, one to none.
The ghost words. The paper mentions prepositions like love.
English loves of,
Mm.
the President of the United States.
Yeah.
But in many languages, Czech, Russian, Latin, you don't use a separate word for of. You just change the ending of United States to make it possessive.
The genitive case.
Right. So the algorithm comes to the English node of
Yeah.
in the tree. It looks for a partner in the foreign sentence. And there's no partner. It's empty.
So does the tree just snap? Do the branches fall off?
No. The algorithm performs a little bit of surgery. It effectively deletes the of node, and then it stitches the cut ends back together.
Teleportation.
Basically.
Yeah.
In English, president is the head of, is its child, and United States is the child of. Since of disappears, the algorithm just grabs United States and reattaches it directly to president.
So the hierarchy is saved. United States still modifies president. We've just cut out the middleman.
Exactly. So now, thanks to this robust, messy alignment strategy, using neighbors, using weak links, handling the ghosts, we've generated thousands of dependency trees for our low-resource language.
But here's the reality check. And this is where the paper takes a turn that I think is really important for anyone working with data. We admitted earlier that we let in weak links. We prioritize coverage over perfection. Doesn't that mean a lot of these projected trees are, well, garbage?
Oh, absolute garbage. Just noise. Bad translations, idioms that don't make sense, metaphors that got mangled. If you take all these projected trees and try to train a parser on them, you'll get a machine that speaks nonsense.
Garbage in, garbage out.
Exactly. And this is where the plot twist happens. Usually in AI, we hear more data, feed it everything, even the noise helps eventually. But Mirchev takes a very different approach.
He goes scorched earth. He introduces filtering. And it is aggressive.
He says, I would rather have a tiny amount of perfect data than a huge amount of okay data. So he introduces two filters.
Let's look at the first one, alignment sparseness. Break that down for us.
It sounds fancy, but it's just a simple ratio. It measures how many words in the sentence pair lack that gold standard intersection link.
So if sparseness is 0, every word matches perfectly in both directions. If it's 1, nobody agrees on anything.
Correct. So Rutschik tested different thresholds, and he found the magic number was Butyl point.
0.2. That's incredibly strict. That means if more than 20% of the words rely on those weaker links, the neighbors or the extinguished links, he just throws the whole sentence away.
He trashes it, deletes it from the training set.
Yeah.
And to give you a sense of scale, they ran this on an English-Czech data set. They started with 100,000 sentence pairs.
A decent-sized data set.
A standard size. After applying this filter, they were left with, get this, 12,500.
Wait, 12 that they threw away almost 90% of their data.
87.5%. Gone. Vaporized.
That feels insane. I mean, that feels like scientific malpractice in the age of big data. How can you possibly learn better with so much less?
Because the 88,000 they threw away were poisoning the well. In this specific task projection, noise is incredibly damaging. A wrong grammatical structure teaches the machine a rule that doesn't exist. It's better to have a small textbook of perfect facts than a massive library full of lies.
I guess that makes sense. It's high-precision learning. If you teach the computer cat, sat, math, Illinois even once, it takes 10 good examples just to unlearn that bad rule.
Precisely. But he didn't stop there. There was a second filter, and this one was even less forgiving. Non-projectivity.
This is the visual one. Break this down.
Imagine you write a sentence on a piece of paper. Now draw arrows from the parents to their children, from verbs to nouns, adjectives to nouns. These are arcs that loop over the top of the sentence.
Okay, I'm visualizing the arcs, like little rainbows connecting the words.
In a projective tree, none of those arcs cross each other. They nest. A big arc might go over a small arc, but they never form an X. They never get tangled.
And if they cross?
That's non-projective. Now here's the nuance. Natural languages do have non-projective structures sometimes. It happens in Dutch, it happens in German. But Mirchek's insight was that in a projection scenario where we're forcing English grammar onto a foreign sentence, a crossing line isn't usually a linguistic nuance, it's usually a mistake.
It means the alignment got tangled. It means we mapped the wrong word to the wrong place.
Exactly. It's a sign of a bad projection.
Yeah.
So he set the limit. The NP max, to zero.
Zero tolerance.
Zero tolerance. If a projected tree had a single crossed wire, a single non-projective edge, he threw it out. No mercy.
So we've gone from 100,000 sentences down to this tiny, pristine handful. We've stripped away everything that looked even slightly suspicious. The big question is, did it actually work?
It did. And this is the validation. They tested this on 4 languages: Bulgarian, Czech, Dutch, and German. They used standard data sets, things like EU laws and news commentaries, and they compared their method against a previous heavy hitter in the field, a method by Gonchev et al.
And Gonchev's method wasn't simple, was it?
No, not at all. It was very sophisticated. It used posterior regularization, unsupervised training, lots of heavy math to try and model the uncertainty. It was trying to be smart about the noise.
And Marichek just used a standard off-the-shelf parser.
McDonald's MST parser, straight out of the box. No modifications to the learning algorithm at all. He just fed it his tiny, super clean data set.
And the results.
On the Bulgarian data, Gonchev's complex mathematical model hit 67.8% accuracy. Marichek's simple projection plus ruthless filtering hit 68.1%.
It beat it.
It beat it, not by a mile, but it won. And the real victory is in the simplicity. It didn't need a new complex brain. It didn't need a supercomputer. It just needed better food.
That is incredible. It really vindicates the whole clean data approach. But I do want to add a caveat here for our listeners because we value transparency. The paper does mention post-processing nuances. It wasn't entirely automated magic, right?
That's a fair point. To get those top scores, they did have to add a few manual rules. For example, coordination structures.
Apples and oranges.
Right. In English, depending on who you ask or which system you use, and might be the head or apples might be the head, it's kind of ambiguous. But in Bulgarian, the convention is strictly that the first member, apples, is the head.
So if they hadn't fixed that manually, the computer would have been marking itself wrong even when it understood the sentence, just because of a formatting convention.
Exactly. There's like losing points on a test because you didn't double space the essay. The content was right, the format was wrong. They also had to tweak auxiliary verbs in Czech. But these were simple rule-based scripts. They weren't retraining the AI. It was more like formatting the output to match the answer key.
Which I think is permissible. It doesn't undermine the main finding.
Not at all. The core finding stands. Divergent alignment to catch everything, followed by aggressive filtering to kill the noise, works.
So, zooming out, we've been deep in the weeds of dependency trees, symmetrization, all these recursive algorithms. What's the big takeaway here? Why should someone listening to this care, even if they aren't planning on building a Czech parser today?
Well, I think it shifts our perspective on low-resource languages. We used to think, oh, we can't build AI for these languages because we don't have the money for data.
We thought the barrier was financial. We thought you needed Google's budget to hire those linguists.
Right. But this shows the barrier isn't really financial, it's methodological. If you have a parallel text, and we have translated Bibles, government docs, and manuals for thousands of languages, you can build a parser.
Yeah.
You can unlock natural language processing for the have-nots of the digital world.
It democratizes the tech. You don't need $1 billion. You just need a clever algorithm and a willingness to throw away bad data.
And that brings us right back to that quality versus quantity point we started with.
It really does. We are so obsessed with scale, trillion parameter models, petabytes of training data. But this paper is this quiet little counter-argument.
It suggests that compatibility is more important than volume. We threw away nearly 90% of the sentences because they weren't compatible with the projection method. And the remaining 10% outperformed the whole set.
It makes you wonder, are we hitting a ceiling in modern AI because we're just feeding it too much noise? We keep hearing about hallucinations and errors in these big models.
It's very possible. We might find that the next great leap doesn't come from a bigger data center, but from a better filter. It might come from curators who really know what to throw away.
Is less actually more, provided the less is perfectly aligned? That is the question we'll leave you with today.
It's a good one to chew on.
Thanks for diving in with us. We'll see you next time.